Okay, so sadly my microphone wasn't on, but I'll have an interesting technique here. I'm going to play it at twice the speed and explain. When you rotate around the x-axis, you're creating a circle. Anything you would rotate around the x-axis. So you're taking this function, you're rotating around the x-axis, you're creating a whole bunch of circles. If you wanted to find the old school version of finding the volume of that, you'd find the volume of the big circle and then the next circle and the next circle, and you essentially just keep adding them up. Or you find the volume of the circles and you multiply it by the height of that cone. Well, the distance between the x-axis and the top here is actually this function. But this is the formula for a circle, pi r squared. And the radius is the distance from the x-axis to the top of this y. Well, that's the function they've given us. In this case, that distance is e to the x. But that's the radius. If I were to rotate around, I have to square it. So really, we can take this pi and put it in front because it's a constant. Really, I'm finding the integral of e to the x squared. And e to the x squared is really e to the 2x. So I have to find the antiderivative of e to the 2x if I'm not going to use a calculator. Well, we learned that the derivative of e to the x is e to the x. Okay? But we have that little 2 here. So the question is, what do I have to take the derivative of to get e to the 2x or e to the x? That x should not be at the bottom, by the way. It should be e to the x to the 2. And we learned that, well, when you take an antiderivative, you're essentially figuring out what was here is going to get canceled and becomes a 2. So for instance, here I'm showing that the derivative, antiderivative of x squared is actually x cubed over 3. Well, here we want to be left with nothing in front. So we're going to try to take the derivative of 2x, e to the 2x over 2 and see what happens. When you take a chain rule, so for instance, if it was just e to the x to the 2 would have to come down in front, and then you have to take the derivative inside. Well, if we do e to the x to the 2 over 2, the 2 comes down in front, it cancels, and I have to reduce the exponent down to the 1. But then I have to also take the derivative of what's inside the bracket. That's the chain rule. And that's e to the x times e to the x, which becomes e to the x squared, which means the antiderivative of e to the x squared is actually e to the x squared over 2. You can do it by taking that derivative of that, and you'll end up with e to the x to the 2 or e to the 2x. Doesn't matter which one you take, e to the 2x or e to the x to the 2, and use the chain rule. Both you have to take the chain rule. You take 2 to the x times 2 times the e to the 2x, and then the derivative of e to the 2x, and you still get the same answer. So that means I have this, so that means I can take the antiderivative here, which is e to the 2x divided by 2, and minus e to the 2x divided by 2, and I can go from minus 2 to 1, because that's the distance here on x, which means I will find the furthest right one, which is 1, and I will take e to the power of 2 times 1 divided by 2, and I will subtract the furthest left one, which is e to the 2 to the negative 2 divided by 2. So that's what I'm doing here. So I have to go from left to right. We can go through it more. So the first one I do is the top number, 1. Well, e to the power of 2 divided by 2, which is what I do here, minus e to the power of negative 4 divided by 2, which is I do there. It's just a calculator. So take e, which is just a number. I discover that it's squared divided by 2 is 3.694. I put it in my memory. Then I take e to the negative 4 and divide it by 2, and I get that. And I subtract the 2, and I get 3.68. But remember, I'm multiplying by pi. So here's a little mistake. Here, I forgot to multiply by pi. And I go up back soon, and I correct it. Okay. But before I go back and correct it, and you have to multiply by pi, it comes to like 10.8. Before I go back and correct it, I verify my answer using Desmos. Okay. Desmos can actually do the integral, but we're going to do both the integral and we're going to do the antiderivative to show that the answer is right. But all these questions are about rotating the function around the x-axis and essentially always squaring the function they give you when it's rotated around the x-axis, and then taking the antiderivative. Here I find we got the correct answer. I made the function e to the 2x, and I found the integral of that, so I don't have to find the antiderivative when I do that. I just make my function equal to e to the power of 2x. And you might wonder, that's the square. And I did indeed get the same answer. So I'll wait till it comes back. Ah, there's where I remember to put the pi in. And there. And my guess is your teacher wants you to multiply by pi and then round up. Personally, we never learned to do that. Pi was far more accurate, so we never changed pi. You can give both answers to make sure you get both correct. It's about to go back to the Desmos. I'm just explaining I forgot pi here. So I'm going to pause. You can see that down here with this g to the x, here I've made the antiderivative to prove that I did the correct thing. And I take g to the 1 minus g to the minus 2, and I get the same answer, 3.6853702302, which means the antiderivative works just as well as taking the integral by letting Desmos do the integral. But then I remember to ask it to multiply by pi, and the answer should be 11.5779. They want 3 decimals, so it's 11.5778. I think I'm just explaining my mistake there. And then I think I'm proving that the derivative of this is f of x. See, I'm taking the derivative of my g of x, which is e over 2x over 2, and showing that the graphs are the same as f of x. In other words, the derivative of e to the power of 2x over 2 is indeed e to the 2x. And now I'm doing the next one. Now in this one, they make the boundaries y-axis, x-axis, and therefore you have to figure out where it reaches the x-axis. Well, it reaches the x-axis, see, because it's big in the beginning at x is equal to 0. When, oh yeah, I'm explaining here that I'm surprised your teacher didn't ask you to rotate some things around the y-axis, which happens, and in that case you have to find the inverse of the function. So you have to learn that. Make sure to ask your teacher if he's going to throw stuff revolving around the y, because it's a little bit more difficult. But all his questions around the x. So it's got the same thing. This end is bigger circle, but eventually it comes to 0, and he doesn't tell you. That graph is not clear. It looks like it ends at 9. You could easily plug in 9, but I believe he wants the boundary to be the x-axis, which is what he says. Therefore, you have to set y to 0 to figure out what value of x, when we reach the x-axis, does this cone stop. So we're going to do it here, I believe. I'm just showing the theory. So we're going all the way until we reach 0. But the question is, this graph looks like 8 or 9. So we have to set our function when y is equal to 0 is when we stop. We set that to 2. That's just the cube of x. So we take a log of both sides whenever we want to solve something that's derivative. Oh, you know what? I didn't have to do that. I could have taken the cube. Sorry. So the cube of, I could have just cubed it. I don't know why I logged it. So I could take a cube of both sides, and the answer is x is equal to 8. I don't know why I did what I did there. It's x is not the exponent. I don't have to take the log. So I could have easily done this. Sorry, I'm going to just stop. I don't know what I was saying. I think I was just doing it quickly. If we're trying to solve this, when is x to the third equal to 2? This is the same as saying the cube root of x. That's what fractional exponents are. To get rid of this cube, I simply square it, or sorry, cube it, both sides. This cube will cancel this, and I get x is equal to 2 cubed. 2 cubed is equal to 8. I don't know why I took the log. The log will still give me the right answer, though. Duh. You only need to log when x is in the exponent, not when x is the base. And then just 3 times log 2 is 8. Oh yeah, this is where I'm showing that we can rearrange the logs to realize that 10 to the power 3 log 2 is what I'm looking for, and I just wasted a lot of time doing that. Don't know why. You can just cube both sides, and x is equal to 8. You get the same answer using the log. 8. So we know it goes from 0 to 8, so now we need to square it. That's something else I forgot to do. I have to square this function because it's a circle is pi r squared, and that's the radius up there. So I think I took the integral or the inverse derivative of what's there, and then I had to backtrack. So I'm just going to go. So what I do instead is I square it. I discovered the square here in the first line in this messy thing. It's just x to the third times x to the third is x to the 2/3. Minus 2x to the third minus 2x to the third is minus 4x to the third, even though I have 2 there. I correct it later. And then minus 2 times minus 2. You FOIL it. Minus 2 times minus 2 is plus 4. I have minus 4 there. I correct all that, fortunately. I don't totally see it's minus 4. So there, I've corrected that. Now I'm doing the inverse derivative. And all you do is you add 1 to the exponent and then divide it by that fraction. So let me explain what I do there. So we're working with, let's go back a little bit, even though I have it wrong here. This is good enough. We're working with this derivative here, and I'll make it more clear. It's x. Oh boy. X to the power of 2 over 3. And then that should have been minus 4x to the third. And that should have been plus 4. Plus 4. Like the, oh, not x, just plus 4. Okay, just bringing this down, making it cleaner. Get rid of some of this stuff. Get rid of this, get rid of this. Bring this up a bit, bring this down a bit. Okay, this is what happens when I FOIL the original function. In other words, when I square it. To find the antiderivative, you have to add 1 to that and then divide by whatever that is. When I add 1 to that, which is 3 over 3, it's 5/3, which means the antiderivative, and because they're all being added, you can just find it. You can just do each individually, rather. It's going to be 5/3 up there. Bring her down a bit more. And it's going to be divided by the fraction 5/3 to get rid of it. Hang on, I'll explain why. When you're dividing by a fraction, you can simply multiply by the reciprocal, like that. Which means the antiderivative, like that. Put this 5 over here. There we go. Which means the antiderivative of x to the 2/3 is this. And you can prove it by taking the derivative of this. You have to bring this down. You have to subtract this by 1, which is 3 over 3. It becomes 2/3. When you bring this fraction down, the 5's cancel and the 3's cancel. You're left with x to the 2/3, which means the derivative of this is indeed x to the 2/3. So that's the antiderivative. This one, you do the same thing. We add 1 to that. We get 4/3. Good enough. You bring this down, and you have to divide it by that fraction to get rid of it, 4/3. Well, when we're dividing by a fraction, it's multiplying by the reciprocal, 3 over 4. I can see that the 4's here will cancel. And I'm left with minus 3, which means the inverse of this, or sorry, the antiderivative of this here is minus 3 x to the 4/3. Like that. To prove it, you take the derivative of it. 4/3 comes down. The 3's cancel. You get 4 times minus 1, minus 4. You subtract 1 here, becomes a third. This is what you get when you take the derivative of that. So that proves that that is indeed the antiderivative. So far I have 3/5 x to the 5/3 minus 4 to the 4/3. And this is the easiest one of all. The antiderivative of 4 is 4x. Now we're looking for the space from 0 to 8. Well, 0 comes out 0. When I plug 8 in here for x, I get 32. When I plug 8 in here, we get the cube root of 8, which is 2. And 2 to the power of 4 is 2 times 2, 4 times 2, 8 times 2, 16 times 3, minus 48. So we get minus 48 plus 32. Now I'm going to put 8 here. The cube root of 8 is 2. 2 to the power of 5 is 1 more than 4. So 2 to the 5 over here, 2 to the 4 over here was 8, 16. We got 32. 32 times 3 is, I don't know, 96 divided by 5. 96 divided by 5, and then I can go back to the rest of the video because that's what it comes out with. And the rest, I did it right. So there we go. I just forgot to record the volume. I had the microphone turned off. So I'm going to just go back all the way to the antiderivative because that antiderivative is kind of messy. Let's see, I'm working on the antiderivative. There we go. I have the antiderivative here, and I'm just substituting it in. There we go. There's the antiderivative. 3/5 x 5/3 minus 3x. You've got to practice these together. Anything that's a polynomial is a very easy antiderivative. You just add 1 to the exponent and divide by that new exponent. Now we know that from 0, it's going to be minus 0. So now I have to substitute for 8, and I do it. So I'm just going to substitute for 8. I calculate it. I get 19.2 minus 48 plus 32, which adds up to 51.2 minus 48 if I add the 32, 19.2, and 3.2 units cubed, but I have to multiply it by pi. So this time I do indeed find what it would be multiplied by pi, 3.2, in case your teacher wants it. And this is the one that's 10 point whatever. And that turns out to be the correct rounding. And it's units cubed. So if it's liters, you can fit 10.053 liters in there. To prove it, this time I do the same thing. I'm finding the original thing, I'm squaring it, and we discover that it's the same issue, and I prove that that number divided by pi is 3.2. Then I prove that our antiderivative works, like I did with the other one. And yeah, all I'm doing is proof. And then I'm showing what g of 8 is. It's 3.2. I'm just times pi, and I'm showing that we got the right answer with our antiderivative. Then I'm taking the derivative of that. Notice it doesn't match the original function, and that's because it's got to match the original function squared. And when I square it, turn off the original function, we see that it's indeed the same graph. Therefore, we did everything correct is what I'm saying. Now, then I summarize the next one because I didn't have time. Oh yeah, you can also ask Google AI to do it. And Google AI will give the correct answer, so long just make sure your functions are right. Now, sometimes they raise the x-axis. They don't use the x-axis. They raise it by 1. That's what question 24 is. It's using y equal to 1 instead of the x-axis. But you could bring anything down by the x-axis by subtracting 1. So you can create a new function, f of x is equal to 3x cubed, is it? Minus 1, and that's where it would be on the x-axis. But I'll show you how to do it when it's at y is equal to 1, even though I don't know why. It's the same thing. You can just lower it by 1 and rotate around the x-axis. But this one is using the limitations of the y, the y-axis, and the horizontal line y is equal to 1. I didn't have time to do it, but I will.